This is my solution for this little linear inequalities challenge that we worked on in class today. It asks us to graph this system of inequalities, these 1, 2, 3 inequalities together, and then find the exact area of the shaded region. So here's my graph, and just to point out a couple things. Sure, y is greater than or equal to -1. That's easy enough. This is the line y equal to 1. I made a solid line because I'm including the points, and then I'm going to shade everything above that. I actually waited to do the shading until I graphed all three of these lines and then kind of thought about the region that I wanted to shade that satisfies all three of these. So that was the first one that I graphed because it was the easiest. This actually, I think, is also quite easy. If you notice, some people like to convert these into slope-intercept form to graph them, which is fine, and sometimes that makes a lot of good sense. But in this particular case, notice that if x equals 0, then y has to be 2. In other words, if I get rid of that term right there, I get 4y equal 8. And so that gave me my y-intercept. And then if y equals 0, then x has to be -4, so that -2 times -4 equals 8. So that's my x-intercept. When y is 0, x is -4. And with those 2 points, I went up 2 over 4, up 2 over 4, and I was able to graph this line. I made a dotted line because in this inequality, I'm not including the points that are on the line. And then finally, a basic slope-intercept form here. The y-intercept is 5 right here, and then I'm just going to go down 2 over 3, down 2 over 3, down 2 over 3, and I get this dotted line right here. And then, of course, I want all of the points that are below this line and below this line, so that's this region, and above my horizontal line here, y equal -1. So here's my triangle. I'm going to find the area of this triangle now. That's the task, and it says exact, which means we're not doing any estimation or anything like that. And so in order to find the area of a triangle, we know that it's going to end up being the 1/2 the base times the height, or base times height divided by 2 if you like. And I graphed carefully enough to notice that these points of intersection happen right along some very nice integer values. And so I'm able to count the boxes and just know that the base of this thing is 15. So that's nice. That helps me out. I know the base now. I just need to figure out the height of this thing. But you can see that this intersection point, it just doesn't happen to be right on my grid for my graph. So I don't really know the exact value where the x and y value where these two lines intersect. And so I can figure that out. Specifically, I need to know the y value so I can know the distance from here to that point. And then I'm just going to add 1 unit to that in order to get the height of my triangle. So the note that I made here is that I need the y value of this point in order to find h, the height of my triangle. And so what I do is I'm going to solve this system. And notice all I did was I took this inequality and this third inequality, and I just wrote them as equalities with an equation. And I gave them numbers over here so that I could reference them later in my solution. So one thing you might notice right away is that you could take this expression right here and you could substitute it into the y value of this, and you would eliminate the y through substitution, and then you'd be left to solve for x. What I did instead, I decided to rewrite these equations in standard form to see what they look like. And sure enough, when you write these equations, both of them in standard form, and really you just got to do some work on the second one, notice that we have a -2x and a +2x. Well, that indicates that elimination is going to be a pretty beautiful way of solving this system. So these 2x and -2x, when I add the two equations together, go to 0, and I'm left with 4y plus 3y, that's 7y. And then 8 plus 15, that's 23. And solving for y, I get 23/7 And as you know, I like to leave my I like to leave my answers as improper fractions. I'm going to have to do a calculation with this in a minute. But let me just say, this is a little more than 3. 21 sevenths would be 3. And this is 23 sevenths. And let me just go over to my graph here and notice that 1, 2, 3, and then a little bit more. That's how many units this y value is according to my graph. So I like this solution, and I'm able to verify it by thinking about going back to my graph for a second and thinking about it. And now I can take that y value, if I want to use it to find the height of the triangle, then what I need to do is take that y value and add 1, because notice the base of my triangle is actually 1 unit below the x-axis. And that gets me to 30 sevenths. 23 sevenths plus 7 sevenths equals 30 sevenths. And then I can go to my formula for the triangle, and I get the area is 1/2 the base times the height. Sorry for that shadow, by the way. And when I plug in the base of 15 that I found just by counting boxes and my 30 sevenths, I get this number, and I just put a box around it. Yay, I got an answer. But I'm going to do one last thing before I move on. I'm going to turn this into a mixed number in order to check my work. And what I notice about this division problem here is that 21 is divisible by 7. It's 3. So imagine if this was 210 divided by 7, then it would be 30. And that would leave me with an extra 15 units up here to get to 225 from 210. So, and that's 2 more 7s gets me to 14. That's where the 32 comes from. And I'm left with 1/7. So 32 and 1/7 is this improper fraction written as a mixed number. And then I'm going to go back up to my graph and I'm going to count the boxes, the whole boxes that are shaded in, or at least more than half is shaded in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. So I got about 34 boxes when I just did a rough count. And notice I counted some half boxes and stuff, but that gives me some confidence in my solution. Roughly, I just counted by the boxes that I found up here shaded in, and there was about 34 of them. Well, really, when you count for all the little half boxes, we end up with something a little bit less than that. But it's very close, and so that gives me. I can just say that I counted the boxes in the shaded region, and there's about 32. So I like my solution of 225 divided by 7.